Hey everybody, in this video we are going to talk about crystals and a little bit of math actually. So what can be a crystal? Well, covalent solids that are crystals can be crystals, metals can be crystals, and salts can be crystals and have crystal structures. There are many crystal shapes, but we will look at three simple ones. The very first one will be simple cubic. And this is when atoms form a cube, and the atoms would be the corners of that cube. So it would look something like that. Now, before we continue, we have to learn about a few things. In a cube, or a unit cell, which is what we refer to as the cube, the corner atoms are considered 1/8 of an atom, because as you can see, 1/8 of the atom is inside the cube, because the atom is a full sphere, but only 1/8 of it is actually inside the cube. Now, edge atoms, or atoms that are on the edge, such as over here, count for 1/4 of an atom. Now, face atoms, or atoms on the face of the cube, will count as half an atom, and center atoms will count as 1 atom. So for simple cubic, we have 8 corner atoms, and 8 corner atoms times 1/8 atoms each is going to be 1 atom total per unit cell. So this unit cell will have 8 corner atoms, but the total number of atoms in the cell will be 1, since essentially you can think of it as 8 cubes sharing that 1 atom over here, and this cube has 1/8 of the piece. So let's talk about body-centered cubic. This is basically a simple cubic with 8 corners, but there's a central atom. So because the corner atoms are 1/8 and a center atom is 1, then the unit cell for a body-centered cubic will have 2 atoms per unit cell. Now, let's take a look at face-centered cubic. The face-centered cubic unit cells will have 6 face atoms and 8 corner atoms. So 8 corner atoms, as you can see over here, and 6 face atoms for the 6 faces on a cube. And since each face atom is worth half an atom, that means that there are a total of 4 atoms per unit cell for the face-centered cubic. And when we split the diagram here into cubes, it looks like this. And this is for simple cubic, as I just talked about. This is for body-centered cubic, and this would be for face-centered cubic. So the difference between these two diagrams is that in this diagram, the atoms are cut apart, while in this diagram, the atoms are kept intact. But if you notice, for example, for the face atom, only half of the atom is actually in the cube, while the other one is sticking outside. So now that we learned about 3 cool crystal structures, let's now do a little bit of math. Now, we have to get a little bit creative here. Silver crystallizes with face-centered cubic unit cells. So this is a face-centered cubic unit cell, and we remember that there are 4 atoms in a face-centered cubic unit cell, and in this case, it will be 4 atoms of silver. Now, the edge of the unit cell is 407 picometers. So this would be 407 picometers. Find the atomic radius of silver. So we have to be a little bit creative here. What is the atomic radius of silver? Well, if you remember, the radius is just half the diameter. So it would be, well, this. It would be this little part over here. That would be the atomic radius. But how do we get that from the edge? Well, we can draw a picture, and we can draw kind of like a triangle, and this will be 407 picometers, this will be 407 picometers, and that's the edge of the unit cell. And if you notice, this diagonal here contains 4 atomic radii, so 1, 2, 3, and 4. So you have 4 atomic radii on that hypotenuse. And notice that this looks like a right triangle because it's part of a cube. So we could use Pythagorean Theorem which states that a squared plus b squared equals c squared. Now notice how chemistry requires math, so be prepared to do math in chemistry, and also be prepared to do some geometry as well. So we are prepared because we know our formulas, and we know that a and b are 407 squared and 407 squared, and c squared will just be 4r squared. Don't forget that parentheses. So now we just have to solve it algebraically. 407 squared times 2, because there are 2 of the 407 squareds, we will get 331,298. And let's keep track of sig figs, 3 sig figs, and this is equal to 16r squared. Now divide both sides by 16, we get 20706 is equal to r squared with 3 sig figs, and we square root this, and we get that the radius, or the atomic radius of silver, is going to be 144 picometers. So not bad at all. It was just a little bit of geometry, and let's do the second part. We have to now find the density of silver. So let me clear all this work so we have more space, and let's write our answer for part 1. Part 1 was going to be 144 picometers for the atomic radius. Now what's the density? Well, the density is going to be equal to the mass over volume. Now, how do we apply it to this? Well, if you remember, density is an intensive property, which means that no matter how much stuff you have, the density will always be the same. So in this case, we could have a unit cell of silver, and that unit cell of silver will still have the same density as, a block of silver, for example. So using that to our advantage, let's figure out the mass of the unit cell and the volume of the unit cell. Now let's do volume first, because volume is fun. So the volume of a cube is going to be the edge cubed, and we know that the edge is going to be 407 picometers cubed. Now, I don't like picometers, honestly. We usually see density in grams per cubic centimeter. So how about this? Let's try to figure out how to convert picometers to centimeters. So 407 picometers times, well, let's convert it to meters first. So I think there are 10 to the 12, okay, that's a bad 10 to the 12 picometers per meter, and we know that there are 10 to the second centimeters per meter. So doing the math, we can see that we are going to get 407 times 10 to the negative 10 centimeters, and we want this in scientific notation, so it would be 4.07 times 10 to the negative 8 centimeters. So let's use this number and cube it. So instead of the volume being 407 picometers cubed, we can make it 4.07 times 10 to the negative 8 centimeters, and all of that is going to be cubed. So let's type that into our calculator, and I got 6.74 times 10 to the negative 23rd cubic centimeters as our volume. So we got the volume. How do we find the mass? Well, we have to know something. We have to know how many atoms are in this unit cell. And if you remember, for face-centered cubic unit cells, there are going to be 4 atoms. So let's use that to our advantage. There are 4 atoms in that unit cell. So we have to find the mass of those 4 atoms. How is that even possible? How can we find the mass of 4 atoms? Well, 4 atoms of silver times Avogadro's number. So we have to think about whether it goes on the bottom or the top. So I think it goes on the bottom, 6.022 times 10 to the 23rd atoms of silver per mole of silver. And we know that a mole of silver weighs, well, let's check out a periodic table. It weighs 107.87 grams. 107.87 grams. Doing the math, 4 divided by 6.022 times 10 to the 23rd, and then multiplied by 107.87, we get that the mass of 4 atoms is going to be 7.16, and there are 4 sig figs here, and that's an exact number. So 7.165 times 10 to the negative 22 grams. And now we have the mass of the unit cell and the volume of the unit cell. So guess what? The density is just the ratio between the mass and the volume. So we can just divide these two. So 7.165 times 10 to the negative 22nd grams over, well, the volume is 6.74 times 10 to the negative 23rd cubic centimeters. Doing the math, we get that the density of silver is going to be 10.6 grams per cubic centimeter. So that's the answer for that question. And if you look it up, the density of silver is 10.49 grams per cubic centimeter. So I'd say that this answer is pretty accurate. And this problem just goes to show how something like the edge of a unit cell can give us the density of silver. So my point is that there are many different ways to find density, and looking at a unit cell is one of those ways. And that's all for this video, and have a nice day.